So this is the thesis defense of Shayne who's been here for, what, 4 years, right? And he started off with Deb Roy's group, where he was supposed to beaver away at NPI, natural language stuff, and then decided he wanted to do bigger questions and bigger things. And the most I've been giving him a hard time here. The most distinctive thing about his CV is that he has an average of 17.73 co-authors on all of the papers that he's done. It's like, how many of you have more than 5 co-authors? Yeah, right. Okay, so there's something very distinct. He's sort of like physics, right, where they have these like huge papers, numbers of authors, but in AI and the roots of AI and how it works. So very distinctive, and as a result, he's done amazing things. Is really sort of a force, and is going to move to the West Coast hopefully after this. I'm sure it'll all go well. So you have to come up there to see him. But I'll be happy to have him out there because I'm most of the time out there. So why don't we begin? We're going to go about 45 minutes-ish.
Yes.
You can ask questions if you're really confused, but then maybe save the more speculative questions towards the end. Okay?
Awesome. Thank you, Sandy. Okay, welcome everybody to my thesis defense. People on Zoom, can you hear me? Do I come through well? Okay, awesome. Welcome, a special welcome also obviously to my committee, Sandy, Sara, and Peter. Thank you for all your support and your mercy, I hope, today. You're all asking, you're here because you wonder, what did Shayne do for the last 5 years? And specifically, why did he need so many co-authors to achieve this? What did all these people's time actually amount to? And did we get anything done? And so I'm going to walk you through my attempts to cultivate, extract, shape, sculpt, scale, scrutinize, and a myriad other verbs, data to turn it into something pulpable, useful, that we might call a resemblance of intelligence. So there are 2 propositions that I would love to convince you of today. They are the themes throughout my work of the last 5 years. The first is that data is the lifeblood, the beating heart that drives AI systems. Whether we talk about massive amounts of text on the web, images, videos, audio, whatever it might be, our endeavor has been to compress them into neural architectures using learning algorithms such that they produce intelligent models. But if you really care about the capabilities of these models, what they generalize to, the tasks they can and can't complete, or their failure modes, their safety issues, and the things you don't want them to do, the first place you generally look is the data. And so it might come as a shock to you that the data behind AI, I would argue, is the thing most well understood among the components on the screen here. Least understood. It is massive, opaque, heterogeneous, and in general, something that we crawl, we scrape together, and we throw into the model hoping that it learns something useful. But for the most part, we don't have a good sense as scientists of how to configure it, optimize it. What are the levers by which to make it useful for us in the model it produces? And the second thing that I want to convince you of is a little bit different. It's that AI's societal impact, the outputs of AI as we deploy it to the world and see how it operates and what it actually accomplishes. If we want to understand that, then we need to understand not AI models, but AI ecosystems. I'm going to quickly set my timer so I can make sure I am not going too slow or too fast. So academics typically think about AI models, probing them in the box with inputs to get outputs. But now we're saying, okay, actually, we should focus more on AI systems, actual products and services with guardrails and infrastructure around them that are serving more than just an input-output model. And increasingly, we think about multi-agent systems that work for us and interact on the web. But really, if we want to understand the societal impact of AI, we need to evolve beyond model system and multi-agent systems to think about ecosystems. All of these agents, as they're deployed in the real world and interacting on behalf of a plurality and multitude of people and uses to understand how that's affecting broader society. So you might ask, what are these two propositions doing in the same presentation? How are they related? And that has been the biggest challenge of me describing how this is one contiguous theme in my PhD. But they are connected. If we look on the left-hand side, the AI training data feeds into AI systems that are deployed. They affect the economy. They affect people. They affect journalists, artists. They affect the structure of the web. But in doing that, they leave a trace, a footprint. They leave data, usage logs, conversation logs. The crawlers leave logs on how they access and who they're accessing. And websites change their structure to mitigate or remove or change how AI crawlers access them. This is big data. This is data that we need to analyze to understand how the world is affected by AI. So whether we talk about inputs, the input data to AI, or the output effects of AI, it is, generally speaking, at least in my work, an exercise in data optimization, configuration, examination, and exploration. And so this blue central bridge are the techniques that I've explored to understand and unpack large-scale AI data, both as input and as output. So the primary endeavor of my PhD has been to develop general data-centric methods to understand and to configure AI. And this has two sides to it. One side is to optimize AI systems, make them better and safer. If you optimize the data through quality and safety filters, synthetic augmentation, scaling, and mixing laws, or you can audit the data for other peripheral legal, ethical concerns to de-risk what might be in there and cause issues downstream once you've trained this big model. And you also might want to examine the AI ecosystems, the data that shows how they are evolving. And you want to evaluate them, not just a model for what it can do and not do and its risks, but the societal risks of AI systems at large, the transparency of the corporations building them, the concentration of power around those who are developing open and closed models, as well as the integrity of benchmarks. And lastly, we might actually want to intervene in these ecosystems now that we've learned something about what's going right and wrong in them. Maybe we should take informed steps to actually do something and make the world a better place, or try to. These are the 4 chapters that I'll talk to you about in the next 35 minutes. Okay, chapter 1. Optimizing data. This is the most technical part of the presentation for AI. So, my first big proposition, assertion that I want to convince you of, is that data is the most consequential design choice for AI. And there are many levers to design the data, to design your AI. One, you want to actually understand the data that you are feeding into your AI, that it is a compression of. You want to then potentially filter it for quality, for safety, use synthetic augmentation or scaling and mixing laws that tell you how much data you should train on for the size of the model, or what proportions of the different data sources you have you should combine and in what ways to make the model as powerful as you can. And my work has looked at both pre-training and post-training data over basically the evolution of steps of training a model to make it powerful. So I'm going to start with my most recent work, Atlas. This was done with some fabulous colleagues, Sneha, Nicholas, Saina, and Sandy, as part of my time at Google as well. And it was presented last week in Brazil at iClear. But the premise of this work is that if we want to understand how to scale data and models together, 99% of the literature out there is looking at this from the perspective of English. How do we train English models for English benchmarks? But what about the rest of the world? What about people that don't speak English? What about data, AI, and sovereignty and having models that represent the various cultures and other people that want powerful systems? And so I look at scaling laws and mixing laws for pre-training. So, okay, let's walk through an example. Let's say you want to train the best model for Thai. Just pick this language out of a hat, but there are something like 90 million Thai speakers. Most of them, it is their primary or highest resource language, so they can't often fall back on other languages. Now the problem is this. If we look at the amount of data available to train Thai models, here is a popular MATLAB 400 data set, and you have trillions of English tokens, or data, to train on. You have quite a bit of Chinese, Spanish, French, but by the time you get to Vietnamese, far less than 26th place, Thai data, you have less than 1%, or actually 0.6%, the amount of training data to train Thai models as you would for English. So what does that mean? That means that a model, we don't know exactly what it's trained on, but generally we have an idea. ChatGPT, Gemini, Claude, or any other models, they're trained generally, mostly with English data. Imagine this is the composition. And then some Spanish and French and Chinese. And eventually, a tiny, tiny sliver of that training data will be Thai. And as a result, these models are not good for Thai or for other low resource languages. Okay, so you might say, well, just train a model just on Thai. The problem with a monolingual Thai model is if you want it to be big, you have to end up repeating Thai data, the tiny amount that you have, again and again and again. And after 4 epochs or 4 repetitions or 8, you get diminishing returns. After 16, you've ceased to learn new things because the model's memorized everything and it's not learning anything new. So the model's also not that good at monolingual Thai. So if you want the optimal model, you should actually have something, and I've looked ahead at the solution, that looks like this. It is training on Thai up to maybe 8, 16 epochs, but then before you saturate that and get too many diminishing returns, you also train on synergistic, helpful languages. Now those might be languages that are close in family, like Indonesian, Malay, Lao, or they might be languages that unexpectedly are helpful because they're heterogeneous and large and have lots of high quality content. That might be somewhat related, like English, Spanish, or surprisingly actually Croatian, which is the HR. That's how you get the best model. But the problem is that before this paper at least, most practitioners didn't have a good way to do this. Okay, so I'm going to walk you on the journey to find that optimal mixture that gets you the best possible Thai model or model in any language that isn't English. So this is a learning curve. If you train models, which many of you here do, basically the y-axis is the loss. If the loss is lower, that means the performance is better. And this is over time, the number of training steps, how much data has been seen by the model. And so this Thai monolingual model, as it trains and sees more data, it gets better and better and better, but eventually kind of plateaus. But now we want to understand how helpful is another language to train for Thai. And so we might say, how helpful is Indonesian for Thai? And so we can train it 50-50 Thai Indonesian, a bilingual model. And we can see it's pretty good. The loss goes down, it gets better, but that's good. What about Thai and English? That looks like this. It's not as good as Indonesian because it's not getting as low as this curve. And then Telugu is the worst. So you get a sense that the distance between these two curves tells you how beneficial roughly one language is for Thai. And the bigger that distance, the worse it is. And so the intuition is that we can measure or formalize a training efficiency gap or training distance that tells us how helpful one language is empirically to another. And very quickly, we can formalize this as a bilingual transfer score. The details aren't that important, but the closer those two curves means that the language is more helpful for Thai and the score is more positive. If we repeat this thousands of times and use lots of tricks to make it more efficient, you get something like this. And this is a massive cross-lingual transfer matrix that tells you, for any one language, how helpful are these 100 other or 38 other languages. So if we look at Spanish, empirically, actually it makes sense. We see the most helpful languages for Spanish in red are, in first place, Portuguese, then Catalan, then French, then Italian, and the least helpful is actually Japanese, which is a completely different script, as well as language family. We can do the same for Thai. We can do the same for many languages here. And the important thing to note is that it's complicated. It's not just what language families are similar. A linguist can't unpack this because it's what data is available on the web in that particular language, its distribution, its quirks. There's a lot that goes into this. Okay, I have a question for the audience. Do you think if Catalan is helpful for Spanish, then it necessarily is true that Spanish is helpful for Catalan? Is there a symmetry there? If you think there's a symmetry, raise your hand. We have 3 people, actually four, some people that are very good at multilingual AI actually are raising their hand. Well, you are wrong. Like me, our intuitions were completely off. Actually, there's an asymmetry because there's more that meets the eye. And it's nuanced and complex, but this was sort of a secondhand observation that I thought was really exciting about this work. We see a divergence where it's not necessarily true that one helps the other. And that's important because so many practitioners could start assuming or speculating that because they're similar or because they did an experiment in one direction, that they can train a model in the other direction, it'll work. Not something you can take for granted. Okay, so we have this huge cross-lingual transfer matrix, and that tells us the synergies, or the scores roughly, empirically, between one language and another, or from A to B and B to A. But this doesn't help us actually know that if we train a model with 50% English, 20% Thai, 30% something else, what the final performance will be. Or to tell us what the best mixture will be given some target language or group of languages. And I want to quickly zoom out for a second. This seems all about multilingual, but it's important to note that you could change languages for different sources that are code and web data or other such things, and the same methods would still apply. So this is more of a general method idea than it is just about multilingual AI. But okay, if we want to actually get the best we want to understand mixture and scaling laws, we have to fit scaling laws. This is where I give you your warning to doze off briefly. There will be 2 slides of mathematics, and then we'll move on to more exciting high-level things. Okay, so some of you might recognize this. This is a scaling law. The chinchilla scaling law has been widely used. And as a quick refresher, the goal of this is to say, how performant will our model be, the loss, according to how big the model is and how much data it's seen. If you have compute constraints, you can't just you don't have endless computers that you can train the biggest model forever on all the data. That would give you a very strong model, but eventually you run out of money in compute. And so you have to figure out, given I only have so much compute, how do I balance the size of the model and the size of the data to produce the most effective, efficient model? And we do that by basically learning these coefficients and exponents that break down the contribution of the performance from the model size and the data size. But we have a problem. This scaling law doesn't really help us because we have many sources of data. We have hundreds of languages, all with their own scarcities and different quantities. And so D, the amount of contribution of data, is one number. It's not helpful. So we need to break this down into 3 sources. The monolingual source, which will be the Thai in this case. The transfer languages, up to K, which will be the highly synergistic or high interference languages. That in this case will be Indonesian, Lao, English, Spanish, Croatian, and Malay. And then a bucket for the other languages that are less likely to have strong interference or synergy. And then we also want to take into account that if you're repeating data from one source again and again and again because there's not much of it, you're going to see diminishing returns. So if you see 4 epochs of a data set, you're not going to see 4 times as much benefit. You're going to see 2 or 3 times. And so we effectively model that with the lambda, learned lambda parameter here. So we came up with this scaling law in order to simplify. We looked at many variants, but have a simple, elegant solution to trying to understand how to scale models and mix many sources together to produce and estimate the best performance. Lo and behold, we do all of this. We get state-of-the-art scaling laws by a massive margin, honestly because not a lot of people are trying to work in this space, but they should be, or labs aren't maybe necessarily publishing, but we released this and we were able then to allow practitioners at various places that have reached out to us to actually compute what optimal mixtures might look like for their models that are not just trying to train a large model primarily for English. There's one last question in this paper we look at that I think is really interesting, and that is the curse of multilinguality. What is the curse of multilinguality that's been plaguing all these linguists for so long? It's that if you have a model and it has 8 languages in it, but you want to add in 8 new languages to the same model, it cannot accommodate well all of these languages at once, and there's degradation of performance across all of them. And so we want to understand how much degradation we are likely to see. And so if we want to increase from K languages to K times R languages, so let's say 4 to 8, R is times 2, what happens? And so to do that, we explicitly created a scaling law that takes into account the number of languages K. We also defined phi inside, understand how those toggles might operate differently according to how they synergize with the model size versus the data size. This also we chose because it can be analytically broken down to compute how much extra compute you would need by increasing the model size or the data size to accommodate more languages without degrading the performance of any of them. And that's this nice formula here. This gives us this nice graph, which a practitioner can look at and say, if I want to multiply the number of languages I have in my model by 2, then to be compute efficient or compute optimal, I should increase the size of my model by 18% and increase the total amount of data I train on by 66%. And that will give you 0 degradation across the languages you have, or at least a close estimate to that according to all the evaluations we looked at. So what is all this bias? It gives developers an ability to estimate compute optimal multilingual scaling and mixing laws, which I think is a massive gap in the literature, and allows users potentially to have strong models built for their own communities, i.e. data and AI sovereignty. I'm going to talk a little bit about another paper done with colleagues at Google. This was a little older. This is Greg, Emily, Catherine, David, and Daphne, a fantastic team that essentially wanted to answer the question, given this massive bundle of pre-training data, other than cutting it up by language, what about all the other ways you can cut it up, and what will be the effects of that? And so this looks at quality and safety filters as well as mixing laws, again, for pre-training data. So you can imagine you have this full pre-training data set, but what if we want to cut it up by domain? We want to remove all the coding data to understand how that will affect maybe academic or math reasoning benchmarks, or remove books, or remove academic data, or remove web data. Or we might want to remove data, various time periods of data. So from 2012 to 2016 or other ranges to understand what the effect of that would be. Or we might want to filter for quality or toxicity at different thresholds to remove more or less content. And what this allowed us to do by setting up these series of ablation experiments is we were able to validate and empirically measure and show that web and books data are the significant levers of performance in a lot of the models that are out there. We are also able to formalize, in this formula down here, a notion of temporal degradation, i.e., if you have one more year of offset between the year of the data you're trying to evaluate and the year of the model that you trained, what do you expect the degradation to be in performance? And even if you have new data to fine-tune, if you didn't pre-train on that year, what will be the degradation? And so there are a lot of moving parts here, but in short, data age does drive temporal degradation, and we can measure and show it and provide methods to actually reliably measure this. And lastly, we showed that quality and toxicity filters can interact with performance in unexpected ways. We actually showed that it helps to upsample toxicity or use an inverse toxicity filter to filter out the least toxic content sometimes, and that'll give you more performing models in many cases for some of the benchmarks we care about. This changes how people think about developing models that are safe but also capable, how safeguards are built around them, and the strategies we use to develop strong systems. I think this work is beneficial for showing practitioners the main levers of performance and safety, what effects they can expect from them, and to develop scientific methods of estimating the value of certain data segments. Lastly, in this chapter, I want to talk quickly about the Flan T5 and Flan collection works with many folks that are scattered now across industry. This focuses on synthetic augmentation and scaling laws now for post-training data. This was early work in understanding multitask scaling, how to scale the number of tasks represented in your post-training data so that your model will generalize to new tasks that it had not seen before. And we also looked at ways of synthetically augmenting task data to accommodate chain of thought reasoning chains And by doing this, models were actually more able to do early chain of thought reasoning and explain and reason, especially over math and coding benchmarks in the early days of instruction tuning. I was really excited. It's rare that Google releases a pretty transparent, open, full suite of models. We were one of the last to release the Flan T5 series, and briefly, it was the most popular set of models on Google, on Hugging Face, and has tallied, I think, over 10 million downloads at this point. But okay, we've talked a ton about the levers of data and how to make models very capable. But what about all the other characteristics of data? So my proposition here is that we have little understanding of the data that powers AI beyond the things that dictate the final performance of the model. And I'll quickly say thank you to all the folks that were part of the Data Provenance Initiative. Many are on this call or in this room. We absolutely could not have done it without you. In particular, Robert, our resident lawyer, Sandy, Sara, and others for advising, and many of the others here. I couldn't list everybody, but here are some of the great contributors and advisors to this project. And part of my 17.7 average co-authors per paper. This was the main inflation because of these folks. So, okay, what data should we use for training? That's a question every practitioner has. And they want to make the most powerful model they possibly can. But there are other concerns that exist. And we released data and we realized this, that because people were asking us, and we realized, okay, there are other concerns. One is, we just talked about languages. Is AI, I think these headlines are very true today as they were when they were put out. Who are these models representing? Is it just sort of the English speakers, or what about the other users of the model? This headline is about Lion 5B, a massive text-to-image, the most popular text-to-image data set at the time that trained tens of thousands of models, the most popular models for text-image generation, and it was shown to contain very sensitive, potentially illegal content that later had to be filtered. That's something you want to know before training your model. Similarly, you've all heard of the lawsuits about intellectual property and copyright. There are many factors that go into deciding whether data is right for your system and however you choose to apply it. People draw lines in different places, and it is better if practitioners and model developers have the capacity to choose for themselves and filter for what they want. And so many of the folks in the Data Provenance Initiative were focusing on how to better annotate the data within massive data sets for sensitive information, privacy, licenses, copyright, terms of use, and there are other things like test set contamination and source tampering, as well as other things listed here. So this work tried to build pipelines to collect all of this information. It was presented, the papers at Nature Machine Intelligence and iClear, and we were fortunate to get coverage from some awesome places to bring attention to the work that we were doing. In total, the team of 50+ people was needed. We had experts from vision, from speech, and from text, and lawyers and policy people to bring together and annotate over 4,000 of the most influential AI data sets on Hugging Face at the time. We built pipelines to annotate complex legal information about the data that had to look well beyond the final collection, but go back through the data sets, the original sources, to collect not just tasks and languages, but licenses, the institutions that created the data, the sources, whether they're machine-generated or human-annotated, the domains, topics, metrics, times of collection, and other important information, such that many people could explore their data, practitioners could filter for the things that they wanted, and also data developers could see what data sets were using the information they'd created. And this dashboard was beautifully created by Nana, who is basically the aesthetic and design person of the whole team and a great researcher who since graduated. But okay, we did all this work, we released all these things. What did we find? There were many things, but briefly, there were some headlines around the amount of incorrect licenses and sources we found on common aggregation platforms that were crowdsourced. We tried to correct that for thousands of sources. we were able to empirically measure the decline in transparency for data and models on a large ecosystem-wide level. And we were also able to show, potentially pessimistically, that over the last 10 years, there has not been improvement in the relative geographic or linguistic diversity of the data sets used to train these models, which is a concern, but also now that we can measure it, something that maybe we can try to improve in the future. But what about the sources beneath the AI data? We're getting all this data from somewhere, and those sources might be changing. And so together we asked this question, which led to a number of, I think, previously unreported findings that captured a lot of attention. It was presented at NeurIPS and sort of widely covered thereafter. And what we did basically is we looked at the most popular pre-training data sets and we sampled the websites underneath them to see where all the data was coming from. And we looked at, over time, how those websites were changing. And in particular, we wanted to understand how restrictions or allowances of access to that data or those websites were changing, looking at something called the robots.txt, terms of service, as well as the different types of websites. And in short, we found the web is fighting back, and the structure of the web is changing immeasurably as a result of AI crawling and AI use. And in particular, we found this big red blob, a massive increase in the restrictions proliferating on AI crawling as websites try to protect against their users and readers and potentially advertising dollars being shifted to AI. We also showed that this is asymmetric. Certain companies like OpenAI are disallowed far more than other ones like Anthropic or Cohere or Meta that sort of fly under the radar, even though their uses might be somewhat similar. We also exposed a story that some people thought they were filtering or they were blocking crawlers for certain companies. In fact, they weren't, because there were unknown or false crawlers out there. And basically, there was a huge mismatch in terms of, or information asymmetry in terms of how information access on the web works. And we showed that it's essentially failing. We also showed that there are rising restrictions, that these rising restrictions mean that there's less availability of trusted, multimodal, and diverse sources of data for those that respect the terms of service or robots.txt, mainly nonprofits, academics, researchers that don't have large exclusive deals with big web publishers. And so this could foretell an increase in concentration of power and other sort of societal larger scale effects in the AI ecosystem. We're fortunate to see this work covered in France, Germany, and internationally. And I think that's because it has many sort of broader implications for how things are changing and not just how things are changing for AI systems. I have the final two but shorter chapters to cover in the last 10 or so minutes. In the beginning of this presentation, I said that we need to evaluate beyond just AI models. And I showed you this diagram where many people focus on evaluating models, or they focus on evaluating maybe AI systems or multi-agent systems. But really, the focus of this work has been on ecosystems, because I think that's where there's a greater absence of analysis and discussion. And so while so many of the benchmarks focus on capabilities, coding, trivia knowledge, mathematical reasoning, or on safety, toxicity and bias, CBRN knowledge, cybersecurity, there are broader concerns with respect to societal risks, societal transparency, concentration of power. And so focusing in on the risks, we looked at, together with some fantastic colleagues at Stanford and Princeton, Sayash, Rishi, Kevin, and others, what are the primary concerns around open foundation models? Whether that be NCII, voice cloning, biosecurity, disinformation, phishing scams, or cyber. And specifically, what is the marginal risk of open models over closed models? Should there be alarmism or not? And if so, in what directions? And this work had a lot of influence, thanks to Sayash and Percy and Arvin and Rishi, on people in the public policy space trying to understand and focus legislative and regulatory attention towards the main risks that AI poses and not the ones that are most hype or speculative. But we also need to evaluate AI models or AI ecosystems for transparency. And so together with a similar team, I was fortunate to contribute to 3 of the foundation model transparency indices, 1 for each of the 3 last years. So at the bottom line, we could actually understand or expose deficits in transparency, apply pressure to companies, and to show where there's a lack of understanding and what the cascading effects of that might be. And actually, this has caused companies to be more transparent and to try to do better on these transparency metrics and to bring better awareness to the community about these systems. And lastly, and more recently, I've done some work on concentration of power at sort of the usage or economic level in open models, done with my fabulous colleagues at Hugging Face, including Lucy, Christopher, Campbell, Atharva, Emily, Irene, Avijit, and Yassine. Not under review. We got into ICML, so if anyone's going to Korea, we'll see you in a couple months. The main takeaways of this work is if you look at this big sort of temporal stack chart here, the red area was Google. The yellow area was Facebook or Meta and an OpenAI. Those used to dominate the open source models that were out there, or open weights, I should say. And then it shifted to Stable Diffusion. And then it's now shifted actually to so much of the community being driven by unaffiliated users and model repackagers. We've also seen this massive blue chunk on the international scale be the US and its contribution to open model use. And instead, actually, it's given way most recently to Chinese developers of DeepSeek and Qwen and others, and the German development ecosystem as well. And we also show trends in development, a move from language models to image generators to now larger quantized multimodal mixture of expert systems. There's a lot of information packed in these ecosystem metrics. We have a dashboard that Emily has created that is, I think, extremely useful to understand where things are going and moving and what the community is doing. Like, there's an explosion of video models that I've seen in the last few months that I think foretells where things are going. There are also broader questions around competition and geopolitics that I think are better answered when you have informed empirical data behind it, and our work tries to bring that empirical analysis to this. Lastly, in this chapter, I want to mention benchmark integrity. I did some work, I contributed some work that Sara and others, Shivalika at Cohere Labs led on the leaderboard illusion to understand how are we evaluating these systems and whether we're using the right evaluations at all, whether there are issues in the leaderboards that everybody is ranking them on, and some unreleased work with Anka and others on looking at real uses of AI and how those are different from what we're actually evaluating, whether that mismatch can be bridged and how. Okay, my final chapter, intervening in AI ecosystems. What does that mean? So George Bernard Shaw in 1903 said, "The reasonable person adapts himself to the world. The unreasonable person persists in trying to adapt the world to themselves. Therefore, all progress depends on the unreasonable people." But George didn't realize that 120 years later, Sara would say something very similar in an article she was quoted, referring to work that we were doing. She said, "Good work isn't just grumpy, it also pursues a solution. It does something about it." And so George and Sara, in that vein, were trying to move beyond just evaluating AI ecosystems, but to do something about it, to intervene, to say, hey, we think something's wrong, and we see a way it could be better. And so to do that, we did some analysis, again, with an awesome set of authors, and Peter really helped on the legal and policy side of this to get this right. But basically, we observed something. We observed that for many researchers, there are obstacles to doing important AI safety and security research on companies. They're concerned about violating terms of service that are quite aggressive and say, if you do this type of research, you're going to be banned, or you might not, there's fear you might not get a job there, other such things. The problem with this is it has chilling effects. It has disincentives to tackle some of the hardest and biggest, thorniest problems that we need researchers focusing on. And it causes imbalanced representation, meaning elite labs are okay doing it because they're well connected, but non-elite labs might be afraid to do this kind of research. And so we borrowed from cybersecurity an AI safe harbor, a codified commitment by companies to protect good faith AI audits, research, and penetration testing. This is something that's well codified, it's measurable, and it's something that you can hold them accountable for. We did something that was a bit scary. We tried to write an open letter on Percy's suggestion. It's scary because you have to rally a lot of people to agree on one thing, and you have to make a big announcement and put it out on X and expect the companies and other organizations and people to tear it apart, but with the support of a lot of incredible advisors, not just supporting it themselves, but evangelizing it and bringing in communities of people. We're able to expand these ideas and get support from CEOs, top industry people, academics, senior faculty, journalists, cybersecurity researchers, and AI researchers, and get coverage in the press as well. And eventually this led to actually having OpenAI change their underlying policies, most of the way to what we wanted, to a partial safe harbor, and to having it directly influence or be codified in part in the EU AI Act Code of Practice. Thanks again to phenomenal collaborators. So we are excited to actually see the things that we think need to change start to actually get momentum. But we realize if researchers are evaluating systems and seeing issues and reporting them, or sorry, they feel now more protected to do this research, they also need to be able to report them. And we found there are issues in responsible disclosure. So then, again, another similar set of authors, but also Avijit and Ruth and Sean, we got together many professionals across cybersecurity and AI security to think about what's missing. And what we found was that when users, journalists, researchers, white hat hackers find an issue, an incident, a flaw in a system that could be very problematic and needs to be disclosed to a company to mitigate, to patch, sometimes they just do not know where to disclose it. Sometimes they'll send an email to one company, but it might not be, there might be 10 other companies affected by this issue. Sometimes they will just post it to social media and pray that it's figured out before malicious attackers take advantage of it. This isn't working. Instead, we are hoping to have a more unified ecosystem and building infrastructure for this, whereby AI flaws can be submitted through one sort of general machine interpretable schematic or report that collects all the relevant information in an easy guided way. And with one click of a button, it can be routed to all of the various stakeholders that need to know, from data providers, model developers, model hosts, model deployers, government agencies, and eventually even the public. Because an informed public will mean that there are safer and more secure systems that are held accountable. We're trying to build this, but it's future work. So in my last 5 or so minutes, I want to summarize. What does all this amount to? I think that it amounts to doing a lot, trying to build a foundation. If we look on the left here, when we talk about computer science and AI, there is a well-established convention of physical computation, hardware, devices, materials in electrical engineering. We have circuits and architectures. We have computational methods and discrete algorithms and optimization. And suddenly, we now also have the learned systems and AI applications. But I think that in between these last two, we need a more principled, more formal, and more foundational brick laid that is data systems and data engineering and optimization. And that's what I hope I am trying to bring in the last 5 years of this PhD. And so we hope to provide more mathematical levers of control over AI through its data. We hope to provide methods to evaluate and intervene in AI ecosystems through analyzing the outputs of AI and its data. And we hope to build a foundation for AI data systems. In terms of the breadth of impact, and this is, I have to say a thank you to so many of the people on this call and in this room, because it truly could not have been done without the 17.7 authors on average per paper. And I will defend this to the end. On the academic front, I was fortunate to be part of 28 peer-reviewed papers. We gave oral presentations, spotlights, we received conference awards, and we gave over 50 invited talks together with many of you. In industry, we released models that were downloaded millions of times, data sets hundreds of thousands of times. We informed Google's pre-training architectures and development. We released widely used evaluations across industry. We released an open letter. We influenced the EU AI Act, OpenAI's own policy. We were invited to the US Patent and Trademark Office, the US Copyright Office. We were featured in 9 major outlets and had wide coverage beyond that. And I think I'm most grateful of all for the community that we sort of built in the Data Provenance Initiative with a persistent set of people nagging one another to do more dirty, annoying auditing work and actually make it a better environment in AI and more informed environment around responsible data and AI system development. Let me give you some other numbers behind the data behind a PhD, or particularly me. 121 unique collaborators. That's how you get this done. They say it takes a village to raise a human. It takes a very educated village to raise one PhD student from 36 affiliations. Thank God for Zoom. 20 countries. I need to measure who's come the furthest today, but it's pretty broad. Together, we wrote 28 peer-reviewed papers. That tallied about 266 figures, 231 tables. That's a lot of figures. These things take forever. They are so annoying. 5 position papers. 4 of these were at the same conference, and Robert accused me of being the position person. If you want a position on AI, I was the person that had it. Every position I have covered. So if you want an opinionated person in AI, I'm your guy. We audited or trained on 4,000 data sets covering 600 languages from 800 different sources. We went to 9 destination conferences. I bunked with some of you, learned your annoying snoring patterns. Some of these were glamorous destinations, some not so much. We gave 62 talks in 5 years. The only thing that produced more hot air than me were the GPUs that I trained some of these models on, tallying almost 2 million hours. I require a lot of management and oversight, 12 separate advisors and managers. Thank you, Sandy, Sara, Peter, many of the others for everything you did to keep me in line or out of line to do this work together. 14 separate emails in the last couple of years from Sandy, just trying to figure out what on earth I'm doing and try to make sure that I'm on the right path. So thank you for getting me there. 7 quirky, goofy, themed PhD parties. You'll see some of those in a minute. 311 mental health runs, and about 600 plus hours at least of sleep debt. These are the numbers behind a PhD. But to wrap up with acknowledgements, I want to start by thanking those that will be judging me next, Peter, Sara, and Sandy. Peter, thank you so much for being, for me, the bridge between, as well as Robert, but between AI and law, AI and policy, getting some of the toughest, most nerve-wracking moments through with the open letter, with the safe harbor work that I think was some of the most rewarding and foundational. You've always been such a thoughtful and dedicated and supportive guide and mentor, despite how busy I know you are running multiple interdisciplinary projects all the time. Sara, thank you for teaching me not just to turn a research project into an initiative and a movement, but for being just a phenomenal communicator, how to deal with stressful situations that can sometimes arise, and for being, how to be a great mentor and collaborator and turn a collaboration into a community and a family and a group. No one does it like you, and I am grateful to learn from you every day. Sandy, you are someone that just constantly backs and believes in your students, and no matter what chaotic journey I'm on, you've been there for me every step of the way and guided and nurtured rather than trying to put walls in my way. And I want to thank you for letting me make some of those mistakes and building me up when I do, and I can't thank you enough, and that's an invaluable aspect from an advisor, so I appreciate, I'm so grateful to have you all in my court. I also had many adoptive advisors along the way, and so I want to thank you all, Daphne, Arvin, Percy, Stella, Sina, Natasha, Deb, you all played an essential role in getting me here. This is back in the C3, the early days, the first year. I want to thank you all for being welcoming of my culture and community with this Canada theme party. We had also an AI model theme party That's Jade. We were dressed as llamas back when Meta Llama was a big thing. Thank you to Human Dynamics. The folks in there, they literally carried me and held me up when things got tough. And then the rest of the time we were in suits, because Sandy would have us parading around the world talking about AI and AI sovereignty and responsibility. Thank you to all of you that traveled with me to present at conferences. This all looks like it's in the same boring warehouse. No, these are all the most exotic locations in the world to present these things. And you are all a part of that with me. Thank you for coming out and exploring these towns and cities with me after as well when we traveled, and for being a bit of the, bringing the fun to the PhD as well. I do not have time to thank you all, but I have to thank Alman and Raj, my roommates, partners in crime and all of this, and many other people pictured here for hosting amazing dinners, going to Suyash's wedding, and doing all sorts of incredible things together. Lastly, my parents have been here every step of the way. An unrelenting support, and it was ironic and a little bit tough when a couple weeks ago, I didn't know if my dad would be here today, but I'm thankful and grateful that he is. And yeah, I appreciate and love you all so much. And anyway, thank you all, and thank you for being on this journey with me. Thanks.
So forth. I think what we ought to do is reverse the sort of questions a little bit. Normally the committee asks first. What I'd like to do is get you guys to ask questions, and then I'm going to chase you all out, and then the committee can have a more intimate discussion. So who wants to start first? I'm a professor, so I can call on you, right? Okay. You're sitting in the front.
I was going to regret that.
Yeah, I know you were.
Do you think that, I don't know, you really got me on the like asymmetry with the languages. Do you think that like that applies to tasks in the same sort of way, right? Like, I often hear lawyers say like, oh, we just need to train a legal large language model, and like Bloomberg's off training, it's like finance large language model. Like, do you think that this asymmetry is something really fundamental about like reasoning capability? And does that make sense? That kind of like legal can learn from English, but English can't learn from legal in the same sort of way, or is it something different?
I'm also going to say I think that's an unresolved question, and I think really hard to answer, especially because the reason will be different across every two sets of data sources. But I think these things interact in a really complex way once we try to compress them into gradients into a model, and we don't know. Yeah, we try to know, we try to get a sense, but I'm going to save that for future work. Thanks, Robert. Great question. Nana also raised her hand, and then we'll come back to that.
Okay. Nana?
Hi, thanks, Shayne. Amazing presentation and events. Congratulations. If not to jinx it, but I had a question. So you had mentioned the importance or how crucial web and books data is, and how it's seemingly the cornerstone of some of these optimal models. And then in the second chapter, kind of reiterated how now, because of robots.txt, that these models are kind of losing access to some of this data. So I'm curious if you had any thought to applying what you had done with the multilingual work of a similar, like as we're starting to see certain data sources shrinking or disappearing, could a similar framework be applied of like what are optimal recipes of training data to account for the losses and disappearance that we're seeing?
Okay, you have to repeat it a little bit so that
Yeah.
everybody can hear.
The question on Zoom from Nana was, given that we see some of the web data being increasingly restricted, can we do sort of a similar analysis with, if I understood correctly, how the interactions between that and other data, the same way we did with the multilingual data, would have effects on downstream models. No, we did not do that because the multilingual work came later, but I think it's a phenomenal question. And I do suspect that we alluded to sort of the lack of trusted sources as journalism is increasingly paywalled and restricted to try to preserve itself. The receding academic content as well, if it's not exclusively licensed by someone. I think that as we see these restrictions increasing, we're seeing sort of a version of the web for humans and a more blockaded version of the web for AI systems. We are seeing somewhat cascading effects, but I would love to do that experiment. I do suspect that you are going to have language models that are a little bit less reliable, a little bit less based on trustworthy information. Hope that answers.
Okay.
Yeah. Ryan, I know you had a, yeah.
So like OpenAI and some other companies are starting to not let their researchers publish at ML conferences and maybe restrict academic collaborations. Just what do you see like the next 5 to 10 years, how that will go, like in this important space of joint industry, academic, legal policy collaborations? Like is it going to get harder and harder to do, or like what comments do you have on that?
Yeah, I mean, it's a great broader question. To the extent that I can answer it, I feel like we are making strides and putting effort to pressure the companies with safe harbors and other things to make it so that auditing them and assessing what they do is easier. As for them publishing, there is legislation in California and elsewhere pushing for more transparency. So maybe they're not publishing their core research or trade secrets, but they can publish more information that will help the academic community keep pace with it. But ultimately, I feel like there needs to be more investment in academia and in these communities so that we can stay stride for stride with the industry. I hope that we don't need these labs to publish in order to do the great research that we can do. And that's going to require grants for compute, grants for longer-term academic projects and not just short-term projects. Yeah, great question. Thank you.
From do you think like as far as like the flaw disclosure aspects, like do you think the EU AI Act, like their Article 73 on like the incident reporting mechanism, like do you think the market surveillance authorities there could almost serve as like a flaw disclosure mechanism at all?
That's a great question. Probably better served for like Cass or Anka that know more about the EU AI Act than I do on that front, or Sean actually. I'm gonna say I'm not sure about that one. Yeah, thank you though. It's a good question.
I really enjoyed the starting with the data-centric methods, implementing, running, doing interesting things, and then you can kind of tell at some point in your program you ran into a wall and had to start advocating for things, and there's this kind of unspoken thing that happens in industry of like you don't talk about data, you talk about models, and but the data is considered more proprietary and also very expensive to acquire and produce and so forth. Do you have any like general guidance that you would give to people moving forward? Like, could you do that language study today, or is it actually are we going backwards? Like, how do you in academia and the publication setting advance the data centrism moving forward?
Yeah, I think that we've taken some steps forward and some steps back. I think there's more shared infrastructure and architecture that has been released to help analyze, curate, optimize, configure data, and like the publications have moved forward. I think we have better understandings, but I also feel that a lot of the data sources like Common Crawl and others have hit roadblocks and obstacles to collecting and curating that data as well for the community. I think that there also are potential future levers to be able to better understand, for instance, how people are actually using AI systems by asking major labs or companies to allow us to run algorithms on those data sets and surface aggregate level statistics information. I think people are being very creative about ways to gain information without looking at things explicitly, and agents can help enable that. So I think that's an exciting future direction. I don't know if that answers part of your question, but yeah.
Privacy enhancing technologies.
Yeah. I didn't know that acronym. I like that. Kush?
What about the distillation attacks?
What about them?
Well, you don't need the training data if you can find out what a good model looks like that's used that.
But seeing what a model outputs doesn't tell you necessarily how people are using it or what it was trained on necessarily. But yes, I think it's another.
You get it to duplicate the results,
Yeah,
right?
yeah. And they're fighting back against those distillation,
course.
you know. We'll see how that pans out.
Yeah. Who else in the back?
Kush and John.
I really, if you don't mind going back to the slide with the substrate and physical layers in data engineering, I really, first of all, great work. I really enjoyed that slide. Sorry to make you go back. And I think, like, when I look at that, like, the AI application data system methods, like, a lot of those things are like sciences. Like, the physical computation is hardware, so look at it as a science.
Yeah.
Circuits, look at it as a science. Computational methods, science. The data systems, you described it as like data engineering optimization, and I feel like what you've done here is kind of like a science, in a similar way economics is a science.
Mm-hmm.
And I wonder if like there's such principles that exist that you have found, other than saying, well, it's, that we can say that like, here's what we want, here's how we want the ecosystem to behave. These are the levers we should play around with, and this is the data that we should go out and collect or get the humans to actually create.
Yeah.
And whether these kind of fundamental laws that exist there, and if they don't, whether you think it's possible to find that.
Yeah, thank you for that question. I promise I didn't plant him. I think that the primary levers mathematically are the scaling laws and the mixing laws. And I think that what new data you should collect or augment changes based off of your target. That's why it's something that it's important that we have a foundational science around it, because the target's moving. What we think we're optimizing for, new bespoke models, coding, agents, it's always changing and developing. And so we need scientific methods that we can, like a packet of methods we can apply and bring to any new case, run them, and it will tell us, okay, here's what to augment, what to filter, what to scale. And that's what I'm trying to build. So there's no sort of like universal laws of the universe, but there are scientific methods that we think generalize because you can pick them up and take them to a new system and application. And I think that's what we're trying to do here. But I don't think this problem would be exciting if we found laws of the, like language is so complex and pluralistic that you can't just sort of put it all in a box. And that's the story of language models, right? So, yeah.
Great work. Maybe a question about the data prop work. So I mean, like the Data Provenance Initiative released a lot of resources, tools. I think maybe one challenge, do you think one challenge was how much it got traction and how much people adopted it, and how do you think you could address that more in the future?
Yeah, so the question, sorry, I should be repeating this for Zoom. In the data provenance work, all the tools and things that we released, one of the challenges was maybe adoption. We did get a decent amount of adoption we can point to, but it wasn't like universal stack. A lot of people still hadn't heard of it that might find it useful. What could we have done differently? I think honestly, a lot of these tools, like it takes persistence that has to go beyond grad students. Like you have to keep building infrastructure, and sometimes years after you know it's useful, eventually, it's kind of like a startup question. Eventually it gets adopted because people find it in time. But I think the key things we did is we released findings, as a researcher should, about the ecosystem. We released methods and released infrastructure that people can and have built upon to repeat the data provenance analyses and audits at scale on, for example, image data sets and others. There are papers at Thesis that do that and are continually iterating. And I think this is a cascade of findings and knowledge about the data ecosystem that wouldn't have been there if we hadn't done that. But yeah, adoption takes time and maybe more effort. Thanks, Shad.
Okay, I think we're sort of at a point where now it should just be you and the committee. Okay? Unless somebody's really desperate for that last question. No? Okay. Out. And thank you for zooming in.